Welcome to the second video on graphing via transformations. In this video, we consider multiple transformations in one graphing problem. A quick reminder from video 1, we had 4 basic functions in our library. We commented in video 1 that we could have a library of functions with dozens of functions, but these are the 4 most common functions that show up in algebra and therefore should be memorized. So we'll call these 4 our library of functions. And we learned in video 1 that if there were math operations done to the inside of the function or the input variable, that there were 5 different cases and rules on how to deal with that. And we also learned that there were 5 separate rules for what to do when these operations are done to the outside of a function. That's essentially what you should know going into this video. The question now, of course, is what do we do when we're graphing a function that's based on one of the ones in our library that has multiple transformations in it? Here's an example. Suppose we were graphing this thing. The first thing that we would want to recognize is that this is the squaring function. And so we would go to our library and recall what the squaring function looks like. But next we would focus on the transformations. And as we learned in video 1, this -2 inside the function, or being operated on the input variable, acts as a horizontal translation. It's going to shift 2 spaces to the right. We discussed briefly in video 1 how that's counterintuitive, but it is a fact nonetheless. And secondly, this +3 added outside the function is going to act as a vertical translation up 3 spaces. And so this graph would be here, having been shifted 2 spaces to the right and 3 up. That's pretty simple, but it does raise a question. And what is the order of transformations? In other words, on this problem, was I supposed to shift right 2 and then up 3? Or was I supposed to shift up 3 first and then right 2? Well, let's examine each of them. If I had shifted right 2 first, notice the gray here. I'll use gray as the intermediate color. If you're not seeing the colors, it's the second one that appears. So this would have been me shifting right 2, and then shifting up 3 would have brought me to here, as you see in green, or the second one. By contrast, if I had shifted up 3 first and then right 2, it wouldn't have mattered, because I would have ended up in the same place either way. Am I suggesting that the order of transformations doesn't matter because you're going to end up in the same place either way? Well, no, I'm not suggesting that in general, because there are times when it matters. This just happens not to be one of them. So if I had done this problem without any consideration for what order transformations are done, I would have got the same answer either way. But there are definitely cases where you don't have to think too hard about it. That's not always the case. So let's think further about order of transformations. We're going to look at these particular 4 problems. We're not going to actually graph them, but we're just going to look at the transformations and what order you would consider them when graphing. In general, first you do any operations that are inside the function, those operations that are being performed on the input variable x. Plainly said, in this case, you would do what's in the parentheses or the radical or the absolute value first. And in general, we then do the outside operations. So for example, on this first problem, you would do the inside operation first and the outside operation second. Although we saw this problem just 2 minutes ago, and I convinced you hopefully that it wouldn't have mattered in this case, but technically inside first, outside second. On this problem here, I would have done what's in the radical first, which would have been a rightward shift of 3, and then what's outside the radical function second, or an upward shift of 5. In this third problem, I would have done what's inside the cubic function first. This would have been a leftward shift 4 spaces. And then everything that's outside the cubing function would have gone second, but the real question here is which one of these seconds would go before the other. It turns out to matter. More on that in a minute. On this fourth problem, notice the absolute value. Notice how there's no operations inside the absolute value. It's just an x. And so these two are both outside operations, so there isn't really any clear direction that I've given you yet here either. So this, of course, raises two interesting questions. What do I do if there's two or more operations inside? What do I do if there's two or more operations outside the function? Let's start with inside. That's a very rare situation. I will have a brief discussion of it at the end of this video, but you're very unlikely to see that in most cases. The real question is the one at the bottom of the screen. What do we do if there's two or more operations outside the function? Well, it turns out you do multiplication first and then your addition or subtraction. Multiplication includes the negation, which is a reflection through the x-axis, because a negation is a multiplication by -1, so that falls under that category. So essentially, what you have here on your screen is the basic order of transformations when you have multiple transformations and you're graphing something based on one of your library functions. So let's take a look at a problem that has multiple transformations and apply the order we just discussed. Here's an example. When given this problem, the first thing that occurs to me is that I have y equals the radical function as the basis from my library that I'm going to use to transform into the function I want to graph. The next thing that occurs to me is the transformations themselves as represented by these operations in green. First, we would consider the operation that was inside the function, in this case, inside the radical. So adding 4 to the input variable x, in other words, adding 4 inside the function, is represented by a leftward shift of 4 spaces from the library function. That brings us over here. Next, I have to do what's outside the function. Doing multiplication before the +1 on the end would be the right thing to do here. So the second thing I'm going to do is consider what happens when I multiply a function by 2. Well, when you multiply a function by 2, you get a vertical stretch by a factor of 2. So I'm going to take the function in gray here and stretch it vertically by a factor of 2. Remember, that means every point that's above the y-axis becomes twice as far from the y-axis as it was on the prior function. And lastly, I'm going to consider the effect of the +1. +1 raises a function up 1 space. And so here I have my final answer for this problem. And while I'm done with this problem, I think now would be a great time for us to remind ourselves what the meaning of graphing really is. Doesn't graphing mean that I could pick any arbitrary value for x, plug it in, get a y value, and then discover a point on my graph or a point contained by my function? Of course, that's exactly what graphing means. It's important to keep all this in mind because sometimes we get so wrapped up in the procedure, shift this way, compress this way, expand this way, rotate that way, that at the end of it all, we forget that we're actually graphing a function that's supposed to coordinate to some kind of reality and what graphing actually means. Anyways, back to the meaning of graphing. Shouldn't it be the case that if I plug in 5 and get an answer for y, that y value would be, or that would correspond to a point on my graph? And yes, of course it is. So I'm going to plug in 5 here. Here's the function we just graphed. You see it in green above. I'm plugging in 5 for x. I'm doing the algebra. Which I won't talk you through, but we do end up getting a value of 7. Okay, so we plugged in an arbitrary 5 and got 7. Shouldn't my function then contain 5, 7? Well, it does, and it shouldn't surprise us. Watch the graph. I plotted the point 5, 7 here. Does that point lie on the graph of the green radical function? It absolutely does. Let's not forget what the arrow at the end of that graph means. It means that this function continues in the same manner as before. And so we do in fact find out that this graph does contain 5, 7. Now, am I suggesting that after you're done graphing something via transformations, that you plot a random point and see if it lies on your transformed graph? Well, I'm not suggesting you have to, but wasn't it nice to see that it did? And isn't that somewhat of a precautionary confirmation that maybe I actually did the work right? In other words, you certainly don't have to do this, but it isn't a bad thing to do to check your answer. Let's take a look at one more problem here from our function library with the 4 basic functions in it. When graphing this, the first thing that occurs to me is that I have a graph that's going to be a transformed cubic. So I go to my library and pull out my memorized cubic. And then I think about the transformations. First of all, notice the negative sign in front of the x cubed. Here's a reminder from algebra. That does not imply that we're cubing the value of negative x. That negative in front of the x cubed literally means -1 times that quantity. And while nobody writes it this way with the 1, the times sign, and the parentheses, that's just not what we do in mathematics. While nobody would ever write it that way, it sure is helpful to think of it that way. Because when you think of it that way, you realize that there's nothing inside the cubic function here. So there's no leftward or rightward shift or any other horizontal motions. What is happening is that I have my 2 transformations outside the cubic. And since one of them is multiplication and one of them is addition, I'm going to consider the multiplication first. So as we learned in video 1, multiplying the outside of a function by -1 causes a vertical reflection, also known as a reflection through the x-axis. And second, the act of adding 2 to a function, so I'm now going to add 2 to effectively to the gray graph that you see there, simply shifts the graph up 2 spaces. And that is my final answer to this problem. So now that we've looked at several examples that have multiple transformations, let's go back to our library and talk about adding new functions to the library. As I mentioned earlier, we could create a library of dozens of functions, including logarithms and trigonometric functions and anything we wanted to put in our library. But I also mentioned earlier that these are the 4 main ones that you're likely to see in mathematics courses and elsewhere. And so they are the ones that we focus on for the most part. But you could really have any function you wanted to put in your library if you were so inclined. And so follow me on this thought. What if someone decided to add a new function to the library? Now, this function does have an equation, and I figured it out myself, but this is way beyond most of the mathematics that we study at the high school and early college level. And so it's very unlikely that you would ever be given this function as a formula. But what might happen probably would happen in most high school and college mathematics courses, is they would give you this function, but not as an algebraic equation. Rather, just by saying that this function, rather than giving you an equation for it, is called some letter. Let's say g of x. And while we don't need to know the equation of this function, you can certainly be given this function and told that its name is g, and be told to add it to your library. And if a teacher or professor adds this function to the library and says this is something you have to memorize, or more likely just prints this for you on an exam, then they can ask you any question they want about it. For example, they could ask you to graph this, or either of these. And when you think about it, these are just ways of asking you to transform g of x. In other words, we could apply the same transformation rules that we applied to our 4 basic functions in our library to any function in the library. For example, this here would, because the -3 is inside the function, we would interpret that as a shift right of 3. This would be a vertical stretch by a factor of 2 because you're multiplying outside the function. And this would be an upward shift of 5. So what I'm trying to say is, if we added a new function to the library, called it any letter we wanted to, like g, we could then ask for modifications of g to be graphed, and you would use the same transformation rules you learned so far in these 2 videos. For example, this would be a shift left 4 because it's +4 being added to the input variable, or it's inside the function. This we haven't talked about, but this is actually 2 transformations, or can be thought of as 2. More on that in a minute. This would represent a vertical compression by a factor of 3. This would be a horizontal compression by a factor of 3. And this would be a downward shift by 4. So all of the same rules would apply to any new function that we added to the library. So for the sake of argument, let's add g of x to our library. We now have 5 functions in our library, the 4 we've been working with, and this new weird-looking function. And let's focus our attention on this particular problem here. Okay, we have one transformation inside the function, the 4 being added to x. That's going to be a leftward shift of 4 spaces, as we know. So that's going to bring the graph over here, as you see in gray. Now the next thing I'm going to do is I'm going to express -2 as -1 times 2. Now that may seem like a weird thing to do, but it's actually going to be helpful because it's going to enable me to think of it as a reflection through the x-axis, because we're multiplying a function by -1, and a vertical stretch by a factor of 2, because we're multiplying by 2. So we're going to consider these as 2 separate transformations. Let's start with the reflection through the x-axis. Remember, I'm already at the gray graph on the left, and now I'm going to reflect that through the x-axis, and I'll get this. Let me remove some of the clutter here so that you can see that this is in fact a reflection through the x-axis. By the way, these 3 points are very important. You'll notice that these x-intercepts of the before and after reflection didn't move, because when you reflect something through the x-axis, any point that's already on the x-axis reflects onto itself. And so I've completed my reflection here. I'll erase the previous step. Now, working from there, the next thing I have to do is do a vertical stretch by a factor of 2. And this will be my last transformation and complete the graph. When I do that, I end up with this. Let me again erase some of the clutter here so that you can see it better. And once again, these 3 x-intercepts are very important. Notice that they're the same for the purple and the green, the before and after. Why is that? Because when you do a vertical stretch, any portion of the graph that's above the x-axis gets further away from the x-axis, in this case twice as far, whereas any portion of the graph that's below the x-axis gets twice as far below in this case. And so these intercepts turn out to be very important for reflections and for stretching and compressing, because the intercepts stay constant under those operations. Well, that was a very tough problem. Here's our final answer. I'll leave it at that. Let's look at something else. You may recall earlier in this video, I promised to get back to the notion of there being two transformations inside or operating on the input variable of the function. I mentioned at the time that it was rare and not something to generally be worried about, and that's true. But for completion's sake, I think we should talk briefly about it. Here's an example of something that has two operations inside of the function. Now, based on everything that we've learned in these videos, one might think that these three transformations that would apply to the radical function would be a horizontal compression of 2, because we're multiplying the variable by 2, a leftward shift of 6, because we're adding 6 to the variable, and a downward shift of 5, because we're subtracting 5 from the function. Well, most of that is true, but not all of it. Let's focus on what's inside the function. Here we're going to use the radical function to graph this transformation, and you can see that inside the radical, or inside the function, there are two operations, the multiplying x by 2 and the addition of 6. Whenever there are two operations inside of the function, for reasons that are very unusual, and you can see in a minute why these don't come up very often, you have to factor out the coefficient of x to do any meaningful analysis on this function. Because only once you've factored out the coefficient of x inside the function can you then interpret them as we would based on all the rules I've presented here. So this would be a horizontal compression of 2. It would be a left shift of 3, and that's the big difference here. There was no 3 in the original function, and still a downward shift of 5. Now, I'm not going to actually graph this function, and these situations are very rare, but I thought it was worth at least mentioning should you ever encounter them. And lastly, I'd like to look at something called algebraic modifications. Suppose you were told to graph this function. Now, we're not going to graph this function, but you might look at this and not necessarily know what the transformations are. We can see that it has a squaring function in it, but how would we modify that squaring function? How would we transform it to graph this new function? Well, sometimes it's not altogether obvious. For example, you see that we're adding 10 here. You might think that there's a shift in some direction, maybe up, of 10 spaces. But sometimes the problems are given to you in an algebraic format that doesn't lend itself nicely to the transformation rules. And so sometimes we have to do a little bit of algebra just to discover what the transformations are. For example, there's a rule in algebra that when dividing two terms by 5, that's equivalent to dividing each of them by 5. There's also, you can also notice here that 10 divided by 5 is 2. But still, there's still a division in this problem. And if you think back over this video and the last one, there was nothing in there necessarily about when you divide a function by a number, how does that transform the function? But there is a rule in algebra that dividing by 5 is the same as multiplying by 1/5. And if you'll notice the 2 plus in front of this function, if we rearrange the order of addition, this looks a lot more like a familiar form to which you could apply the transformations. At this point, you would probably deduce that there's a shift to the right of 3, a vertical compression by a factor of 5, and a shifting upward of 2. Now, I'm not going to actually graph this function, but the point is, there are instances where you have to do some algebraic modifications just to even see what the transformations are in the first place. Let's look at 2 more of these. Here's a graph. It clearly has a square root in it. So we're going to take the radical function and modify that or transform it. But how? Well, one thing that you could do to these to make it look more familiar is to reverse the order of the terms. And then that way you can think of the subtraction in front of the radical more as a multiplication by -1. Either way, the subtraction is multiplication by -1 and then addition, but by rearranging the terms, it's easier to see what this function is in a transformative sense. But now we can see that there would, because of the +4, we would shift left 4. Because we're multiplying by -1, we would reflect through the x-axis. And finally, because of the +3, we would move the radical function up 3. Again, the point being, not all functions will be given to you in a form where it's totally obvious what the transformations are. And so you'll have to do a little bit of algebraic tweaking to get that to become more obvious. One last simple example. If you were asked to graph this function, you would know it would be based on the transformation of the absolute value function. Again, we could use the fact that dividing by 2 is the same as multiplying by 1/2. And then once we saw that we were multiplying the variable inside the function by a number less than 1, we would know that it would be a horizontal expansion or a horizontal stretch of the original absolute value function by a factor of 2. And that completes this video on graphing via transformation and this 2-video series.